Hello, guys. You're welcome to a wonderful time with you guys again. I want to spend time in analyzing work, energy, and power. Yes. Now, what are the things we want to learn in this video? We want to look at definition of work. We want to look at work done by a force inclined at an angle, specifically to the horizontal. Then we want to look at work done by variable forces, by variable forces work done by variable sources. They want to look at definition of energy, then classification of energy. Basically, for this part one of this video, we are going to be looking at uh, kinetic energy and potential energy. So as we listen, God bless you. Now let's go. Now, what is work done definition? Basically, work done is defined as the product of force and what and parallel what distance. So it's product of force and parallel distance. So if I use the word parallel, I don't use the word perpendicular. Be careful with that statement. Now, don't forget that it apart from that, mathematically we can write it as mathematically work done is equal to what? Force dot distance. So that means work done is the product of force and distance. And if you want to say, what do we say? The XI unit or the unit of what? Of work done is equal to the unit. Let me put the word. The unit of work done is what? What is it? This force is measured in what? Newton. Then distance measured in what? Meter. So 1 Newton meter is equivalent to 1 joules. Is equivalent. 1 Newton meter is equivalent to 1 joules. So that means if I say Newton meter, 1 Newton meter, 4 Newton meter is equivalent to 4 joules. So because it's a scalar, why do we use 1 Newton meter as 1 joule? Because work done is joules is a scalar unit. So work done is scalar quantity. Is a scalar quantity. Work done is what? Is a scalar what? Quantity. What is a scalar quantity? A quantity that has magnitude but no what? Direction is what we call scalar. Another thing again I want you to understand again about it is that not only that we can have a force that is acting at an angle, sometimes it can be force can be acting at what? It can be that, look at this, what I'm saying now. Look at the force here and look at the distance move. Let's say move from here, move to this point here, having a force F. So this is distance it covers, D, from here to this place. Now, but there are some cases where we have, that's the case of this. What about if you have something like this? Look at the board. Let's say we have something like this, and we have a force applied like this at an angle theta. Now, automatically mean this mass M. Now, if you want to calculate the work done, let's say you move it from D, you move it some distance D from this point to this point. So that means the force is CF here, distance. Now, it's no longer here now. That means it has moved it from distance to point, this point here, same M. Now, what do we have here? For us to resolve the work done. The work done is not, there's no work done in the vertical direction. Because why? This vertical direction is perpendicular to the distance moved. So you cannot use this resolved direction, this vertical one. There's also, we say work is not done in this direction. Now, what is work done here? is done in this direction. If I resolve this force along this direction, what do you have? Let me clean this one now, since we now see it. So if I resolve it, now the one F, what do you have? F cos theta. If you resolve it to the what? Horizontal. F cos theta. Now, what is the, if you resolve it along your F cos theta, so the work done will not be what? F cos theta, which is the parallel force, the force applied, times what? Distance or dot distance, anyone. Now, this is the work done when it is what? Work done by a force inclined at an angle. But listen now, there is no friction here in this particular system. We assume that the system is what? Is smooth. What about a case where we have what? A friction force. And in this case now, we want to look at it in a way that it will be pulling the body either above or below. Pulling above or below. Now this is the mass. Let's assume it's pulling above with a force F at an angle theta. Now let's assume this is not is a rough surface. This surface is rough. And we have a what? The frictional force here, mu n. That is frictional force. Coefficient of friction times normal reaction. Now the weight of the body will be acting down, which is mg normally. You know that. Now, since the weight, excuse me, since the weight is acting downward, now the normal reaction will be acting upward. Normal reaction is upward. Now, if you resolve this particular force in the horizontal direction, you have what? F cos theta. F cos theta in the, what about in the vertical direction? Why? Because the angle is inclined to the what? To the horizontal. So since it's inclined to the horizontal, here become cos. Why here will now be what? F sin theta. So how many force do you have acting upward now? 2. 1, 2. How many acting downward? 1. How many acting backward? 1. How many is acting forward? 1. Now, in this case, we assume that it moves a distance with a uniform speed or uniform velocity, as case may be. Now, if you are moving a uniform velocity, don't forget that summation F along the x-axis is 0 and summation Y along the what? Vertical is 0. Summation S along the horizontal is 0, summation Y along the vertical is 0 because Y is moving it with a uniform velocity covering a distance of d. Now, if we want to now solve it, resolving along the what? Vertical is 0, we are going to have what? N plus F sin theta is equal to what? What is downward force? Mg, the weight. That is, we have total upward force equal to what? The downward force. Now, what about in the horizontal direction? Sigma Fx equal to what? 0. What do we have there? We have what? Forward force is what, class? Then we have F cos theta is equals to what? What is our, this there? Backward force is mu n. Now, I want to make n the subject of formula here. So what is n? N equals what? Let's call this one 1. Let's call this one equation 2. So what do we do now? We are going to have it as what? F from equation 2, we are going to have F cos theta over what? Abi? So if you now add it, put it here. Let's call this one 3. Substitute it into this equation, we are going to have what? F cos theta over mu plus what? F sin theta is equal to what? Mg. Abi? So what do you have now? What is common? F. We are looking for F now. Into bracket what? Cos theta over what? Plus what? Sin theta is equal to what? Mg. Now what do you do? Find the SCM now. So if you look for the SCM, what do you have? Yes. What is the SCM of 1 and mu? I would have mu, Abi, is the SCM. So mu divided by mu, it was what? Coefficient of friction. We have 1. 1 times this cos theta. Please just listen. Now, mu divided by 1 is what? I would have mu sine what? Theta. So what do you have now? F equal to what? Mg. Now, in making what? F the subject of formula, what do you do? Multiply all through by mu, abi? So that you have what? F cos theta plus what? Mu sine theta is equal to what? Mg, abi? Mu mg, abi? If you multiply all through both sides by what? By mu. So that this one can be multiplied by mu, then multiply this one by mu, abi? So that this will cancel this now, abi? So what do you do? Divide both sides by what? So F equal to what? What now be what? Mu mg divided by what? Cos theta plus what? Mu sin theta. Now, this formula I just gave you now is what? If they ask you that the body is pulling above, maybe the force applied is what? Pulling above at an angle of theta, the horizontal, or pushing what? Above. So if the force is pushing, look at it, pulling above and pushing above is what? Are the same. So if the body is, if I draw a parallel for this here, I put the body here, you see that it's pushing from back. So that means if I'm pushing from the behind, it's also the same thing as pushing what? Pulling above. You know, you can only pull from the front, not from back. So now, but let me give you a shortcut. If you are solving for pulling below or pushing below, use minus sign. Yeah. So that means the force for what used to calculate, the force used to calculate for pulling below, use minus sign. Or pushing below. This one is for what? Pulling below or what? Pushing what? Below. So if you want to calculate what? Pulling below or pushing below, you use what? Minus sign. But when you are using pulling above or pushing above, use plus sign for this formula. Your mass, this one now, don't forget, mg is equal to what? Weight. This one is angle of inclination, this angle. This is coefficient of friction for the surface. They will give you coefficient of friction of the surface, be given to you. So take note of that. Now we are in the we have analyzed what? Work done by what? By force, inclined at an angle, maybe a smooth surface, we have talked about it, which is work done is F cos theta times distance. Then when it is acting at an angle for rough surface, pulling above is plus, pulling below is minus, pushing above is plus, you use here for the same formula, pulling below is what? Minus. Now let's see, because we don't want to prove the other one again and waste our time. Now let's see the work done by variable forces. Let's say we have something like this. Let's say the body, let's say we have a force here applied. Let's say this is a compression force. When the compression force is applied on a string, what happens to it? It becomes what? It reduces the extension. That means the final length is now lesser than what? The initial length during compression. But during extension, what happens? The final length is higher than what? The original length. Now let me even draw something like this. Now if you plot a graph of what? If you plot a graph of F against extension, let me show you something like that. Provided the elastic limit is not exceeded for an elastic material. For example, let's say we have a what? Body here. Beam force is applied to it. F. So you can drag, you can slide the body mass. Now, if you plot the graph of force against what? Extension. Now, what do you have? What I want to have now is that look at the board. I want to have it a what? Straight line graph. Now, what do you notice? You understand that the graph started from the origin. I shade it. Let me shade it. Now, this place, let's call it F1, and let's call this place the highest point here. Let's call it F2. Now, if I want to calculate the force here, the total force, which is the what? The height. What do you have? The height becomes what? F1 plus what? F2 over 2. The height. That means this and this. Don't forget F1 is 0 because it's starting from the origin. Abi? Is it not? Yes. Then our extension, that means the height. Our base like what? The base is like E. If you want to use what? Area of triangle. Because that graph is looking like triangle. Is what to what? Half base times height. Which is equal to what? Half times what is our base? E times height. Height is what? F1 plus F2. So F1 plus F2 divided by 2 is what we call the average force. Average force. So, and if you check, F1 is 0, but F2 is what? Is not 0. So since F1 is 0 and F2 is not 0, what you're going to do now is that if you put in there, you're going to have half times what? Let's say F1 is 0, 0 plus what? F2 over 2 times E. What do you have? 1 over what? 2. Sorry. This is average force. Average force will, that is, if I'm using what? This now, I'll use half times base. The base is what? I will not use over 2 again. Sorry for that. Over 2. Because the base is what? The height is from here to this place. So which is this plus this. Or some people will say this minus this. Because this one is starting from 0 now. That's why it does not count. No, Samuel. So now, if I even say I remove this, let me say what? Look at the board. Let me remove this one. What is the height? I want to show you something. The height is what? F2 minus F1, which is F2. Now, if you want to use it, look at the board, please. In other words, half what? Let me clean this part so that, in other words, half base times, what is the height now? F2. Now, what is F2? F2 is the force applied, which can now give us half. I can write that F2 times what? Extension. So, meaning that half Fe, that's what that happens. Let F2 be equal to our F. You now what? Know that work done in that string is equal to average force F2 times E, which is equal to half Fe, or know fully well for string F equal to what? Ke, the sake of that. For string F equal to Ke. So if F equals to Ke, let's substitute here. What I have? Half times what? Ke dot E. So that means work done is equivalent to area here. So work done finally is equal to what? Half what? Ke square. So this is the work done. Listen. Now this force that we just solved now, 1 over 2 F2 or 1 over 2 F is what we call the average force, which is gotten from what? You can still get that force by what? F2 over 2, which you got, is gotten from F2 plus 1, F1 over 2. So F1 plus F2 divided by 2 give us F2 over 2, which is F1 is 0. So this is what we call the variable force that is acting on the string. So in that case now, that means even in this string, you can vary the what? The force. And as you vary the force, what happens to the extension? The extension change. Look at it, the force is changing. It's increasing now from here to this place. It's increasing, it's varying, it's changing. That's why we call it the variable forces acting on the body. As the force is changing, as it varying, what happens to extension? Extension also change now. Because according to Hooke's law, this is Hooke's law. He said the force applied for an elastic material is directly proportional to the what? Extension, provided the what? The elastic limit is not what? Exceeded. What is elastic? What is extension? L minus L naught. Nabi, what is L final length minus what? Original length. So that is just that. So that one is done. Let's move to what? So take note of this. Now let's go to energy. Definition of energy now. What is energy? Energy is the what? The capacity to do work. So that means that work is what? Is force is what required to do work. So force is required for work to be done. And work done brings about what? Energy, which will, because the work transferred now lead to what they call energy. That means force is required to do work. And when work is now being used or utilized, energy will come into place. So intimately, energy and work are what? Are the same. That's why we say work done is energy is the ability to do work. So and it's also measured in joules. Abi? But let us look at some classification of energy we want to look at, which is we want to start with kinetic energy, potential energy. Maybe in our next video, we look at what? Gravitational what? Other kind of what? Energy. Now, the next thing to discuss under classification is what? Of energies. Let's talk about kinetic energy. So what is kinetic energy? Kinetic energy is the energy possessed when a body is virtually in motion. When a body is what? Is virtually in motion. That means that when a body is on motion with a particular velocity, the energy that is possessed is what we call kinetic energy. Let me say work done equals to what? Let's say work done is equal to force times distance. That means that work done is equal to what? MAG. Listen up. Now, don't forget that from motion, V square equal to what? U square plus what? 2AD from motion. So if you make D the subject of formula, what do you have? Or make AD the subject of formula, what do you have? V square minus U square, look at it now. Bring it here, abi? Equal to what? 2AD. If I go start by what? 2. If I go start by 2, what do you have? So AD is equal to what? V square minus U square over 2. Now let's replace what? This MAD, because F is equal to mass times acceleration now. So let's replace it there. That means replace this one. I want to have what? Work done equal to force and distance equal to what? M into bracket what? In place of AD, I will have what? V square minus U square over 2. And what is this one called? It's simple as half mv square minus what? Half mv square. So in that case, work done is equal to change in kinetic energy. This is what we call change in kinetic energy. Now, why do we call it change in energy? This is what we call the kinetic energy final minus kinetic energy what? Initial. So change in kinetic energy K is equal to work done. Let's take of that. But listen, when what? A body start from rest. When a body start from rest, what happen? When a body what? A body start from rest. From rest. That means U equal to what? 0. Yeah, put U equal to 0 here. That formula becomes what? Work done equal to what? The change in kinetic energy now becomes what? Half what? mv square. This is the formula for kinetic energy. That is proper formula for kinetic energy. Now listen up. What about if you have different objects with different masses and different what velocity? That means two objects now. We have two objects that have two different masses and two velocity. What do you do? Now, okay, that means if their kinetic energy is constant, have m1 v1 square equal to what? Have m2 v2 square. That means two bodies with the same kinetic energy but varying mass and what? And velocity. So what do you have? If you bring the mass here under, bring velocity under, I would have what? M1, sorry for that. Let me change my marker. M1 over what? M2, because this we cancel this, equal to V1 over, no, this will come here, make a V2 square, abi, over V1 square. So if I take square root of both sides, what do you have? Square root of what? Don't forget that this one is if there are indices, if that V2 over V1 or what? Square, abi. So because square is here, you can make. So if you take square root of both sides to remove this one, what do you have? M1 over M2 equal to V2 over what? So final velocity, V2 velocity rather, for the second velocity of the second body. You can take this one here. Now the V1 square root of what? M1 over what? M2. Take note of that. If you have two bodies having the same kinetic energy. So the last one I want to talk about now, that is what? And don't forget that when a particular catapult is fired, if a catapult is fired, like if you fire a catapult, it has been converted. The motion of the stone fired from the catapult is equal to what? Elastic what? Potential energy. This is what we call elastic potential energy. From the energy stored in the string, it's elastic potential energy. We can call it Ke square. The same thing. So please take note of that. That means when a catapult is fired, you are going to stretch the string of the catapult now, to fire, to kill a bird. Then you put a stone inside. Now that stone will be set on motion. The energy produced by the stone to be on motion is what? Kinetic energy now. Then what is the energy put to draw the what? To extend it? Is not elastic potential energy. So that is it. So that is the relationship. Now let's go to the last one, which is what? The last one is what? Potential energy. Now, we want to talk about the last one, which is potential energy. First of all, in a string, we have what they call elastic what? Potential what? Energy. I've talked about that one before. And what is elastic potential energy? It is equal to half what? What? Fe, or we have it as half what? Ke square, or what you call half what? F square over K. Now, how do you get that one? F, this one is what? F over K. E is equal to F over K. So if you substitute it here, you are going to have this as your word. Because let's substitute, you see, half K dot what? F over K all square. So what do you have? I want to have what? Half K dot what? F square over K square. Nabi? So this one cancel. So these are the three formula for elastic what? Potential energy. The next one is what we call what? But don't forget, potential energy is energy possessed when the body is virtually in motion. In position rather. Potential energy, I believe you still remember that. Energy is what? Energy possessed. Energy what? Possessed when what? A body is what? Virtually what? In position. It can also what? Be possessed when the body is raised above a particular height from the sea level. Don't forget that sea level is a reference what? Level for all what? All height. Sea level is the reference level for all heights. So what do? We say that what? That since potential energy must what? Is the energy position for a body to be in position. Now let's take what we call gravitational what? Potential energy. Let's look at energy in a vertical motion due to gravity now. When the body is dropped from a particular height to the ground, let us look at energy from different position. Let's say this is the ground level or sea level. This is A. Let's call this one B. Let's call this one A. And let's call C at the middle. Let's say C. Don't forget that mechanical energy, what is mechanical energy? Mechanical energy is equal to what? Potential energy plus what? Plus kinetic energy now. Abi? So in that case now, what at this point, don't forget that this is a conservative what? System. Now we are going to talk about that. In a conservative system, as one is increasing, the other one will be decreasing. As one is increasing, the other one will decrease. As this one is increasing, this one will decrease. That's at work. Now let's call this one the maximum height. And if we call this one maximum height, class, what do we call this? V equal to what? 0. That means at the maximum height, the final velocity equal to what? And at the lowest level, initial velocity equal to what? And it's hitting the ground with what? V. Now, what is the potential energy here? The potential energy here is what? Maximum, which is equal to what? mgh at point A. Then, what is kinetic energy? Kinetic energy at point A is equal to what? 0. Don't forget. Because at this point, V equal to what? 0. Now, what about at the lowest level? Potential energy is equal to 0. Why? Because the H here at B is 0. Does it have the height? No. And you don't forget, basically, potential energy is equal to what? Mg what? H. So in that case now, at the point C, what happened? Okay, at point B, what happened? So kinetic energy is equal to what? It's equal to half mv square. And it's what? Maximum. Abi? It's maximum. So this kinetic energy is maximum. Let me put it this way. U equal to 0. Potential energy is 0. While kinetic energy is what? Maximum. And it's equal to what? Half mv square. Now, what about at point C? Both is what called mechanical energy. Although, how do we calculate something? Let me show you something here. This one now is, let's say it fall a height h. HC. Let's say this body fall a height HC. Then I say find the what? The potential energy at this point. What is potential energy at point C? So, in that what? PE at point C is equal to what? What do you have? Now what? Mg. You now look for, you remove the what? This small one from the what? So what do you have? H max minus what? That is potential energy for you. Because you need to know the height from here to this place now. That's what you use to calculate potential energy. Then, how do we calculate the kinetic energy at C? The kinetic energy at C is half what? Square. Half mv square. At C is mv square. So, what do you do now? You can equate the two because energy is still conserved. How many? You can say half mv square at C should be equal to what? Mg what? H maximum minus AC. Now, look at the board. I want to do something. Now, let me put it this way, so I can understand. HC, let me put it this way. Now, let me put it. Do you know mechanical energy at point A? Mechanical energy at point A is equal to what? mgh. Let me put it that way so that I can understand. Mechanical energy at point B, the lowest level, is equal to what? Half mv square. You see where question can come out now. Now, if they ask you, mechanical energy is converted to potential energy at what point? At what point? A. Mechanical energy is converted to what? So potential kinetic energy at what point? At the lowest level. So at the highest point, mechanical energy is converted to potential energy. At the lowest point, mechanical energy is converted to what? To what? Kinetic energy. So now, what about what? That means mechanical energy is constant. Now, what about mechanical energy at point B? I want to ask you, point C. Is it not going to have potential energy at point C, abi? Plus what class? Kinetic energy at point C. Now, do you know that mechanical energy at point A is equal to mechanical energy at point B is equal to mechanical energy at point C? Do you agree? Abi? So if I now want to ask something here now, you can equate at point C is this one, abi? At point B is what this? At point A is what to this. Let me take any one. That means I can say mgh at A should be equal to what? Half mv maximum at point B. Because mechanical energy is constant. There are three parameters that is constant here. Number one, acceleration of the body, which is g, is constant. It's moving towards gravity. Number two, the mass of the body is constant. Number two. Then number three, the mechanical energy is constant, which says that it's a conservative system. Energy can neither be created nor destroyed, but can change from one form to another. So in that case, it's not the what? What is what? Mechanical energy at C. Combination of the two of them, abi, which is potential energy at C, which is what? Which how do you get mg what? H max, abi, minus hc, abi, to get the height from here to here now to know. No, always the height is always measured from the ground now. Plus what? Half what? mv at c square. Is not true? Yeah, so that is it. I can use anyone to calculate my this thing. So this maximum what? If I want to use this one and this one, I can use this and this. I can use this and this. Anyone you want to use, can use to calculate. Abi? So let's take it as what? The general formula for this particular one. So I believe that you understand it because this is the basic thing we need to understand from there. Then when we see the last one we want to look at is what? Is well, potential well. If I have a well like this, class, last one, and this water is what? This is water. Look at the one, last one. This water is something H2 deep. Look at it. Now, Samuel, if you look at this now, or David, if you look at from here, let's say the object is here. We want to know the potential energy of this object. Let's measure it from what? We are going to take this bottom as our reference. The bottom of the well. Let's assume from here to this place is what? H1. How do we calculate the potential energy of this body at this point? It's just for you to say potential energy at what? Let's say at A, inside the well or inside the this thing. Potential energy at A is equal to what? LGH1. It's as simple as that. No need to waste your time and begin to just multiply inside the well. You can do so many things. You can still say minus H1 because inside the well minus H2. You still get the same answer. I mean minus, sorry, you calculate from here to this place. Now see H, you calculate from here to here. Then remove it from this one, you still get H1. So why are you not bothering yourself? So just go straight to the point by multiplying the mass of the object that is given to us, the gravity that is acting on the water, and the H1. So that is just that. So we are going to meet in the this part 2 of this class. It's a very technical class. So that when we come, we are going to talk about gravitational potential energy that will be discussed in detail. So I believe that after discussing everything, we watch the video, and when we come to questions, we will get everything we have discussed. Please ensure you subscribe and like the video. Thank you very much for watching. God bless you.